Hello everyone. In this video, I want to talk about the integrated rate law. Whereas last time we looked at the last videos, or the first videos we've been looking at have been called the differential rate law, or just called the rate law. And that's how rate is a function of reactant concentrations. This integrated rate law, which I've underlined in green, is how the concentration is a function of time. So as time progresses, what happens to concentration? Well, we know it goes down, but now we're going to compare concentration brackets versus time t. Okay. Now, the most important thing whenever we're doing this integrated rate law is that we want to look for the straight line. We're going to graph the concentration versus time. Whenever we find a straight line, that's a big smile because that it indicates to us what rate law this is. Here's the integrated first order rate law. So it's the natural log of some concentration A at any time is equal to the negative slope times time plus the natural log of the initial concentration of that reactant. Okay, so we just notice this is y equals mx plus b. Easy, okay, not too bad. And notice, as I mentioned down here in red or orange or whatever color that is, if the graph of the natural log of a versus time yields a straight line, that rate law is first order. And notice here, it's hiding behind that. Notice it's a negative slope, guys. It's a negative slope. And that's because of this right here, the negative slope. Okay? All right, so let's take a look at this. Let's do one of these calculations. We'll save that one for class. So here we have the decomposition of N2O5 is in the gas phase was studied at room temperature, and this is what it is. And there's the reaction. And the following results were collected. Now notice the data looks different than what we looked at before. Now we have a concentration of N2O5 versus time, which is exactly what I said it was. So as time progresses, the concentration seems to go down. Now we know that's going to happen, and it seems to go down at a decreasing rate. Okay, so this is somewhat exponential, but again, we're not going to worry about the exponentiality because we're not dealing with calculus here. So let's look down below here. It says, using these data, verify that the rate law is first order in N2O5 and calculate the value of the rate constant where the rate is negative delta N2O5 over, that should be delta T. Whoopsie. Okay, so anyway, let's take a look at this. So let's verify that this is a first order rate law. Well, we know that the first order rate law says that the natural log of the concentration of N2O5 at any time is equal to the negative K times the T plus the natural log times the concentration of N2O5 initial. Okay? So I'm comparing natural log versus time. So here's time. We're good there. The problem is we don't have natural log, so we have to make a whole nother column of data of the natural log of N2O5. N2O5. Okay, so what we do is get out our calculators, use the natural log button, type in ln 0.1. That gives me negative 2.30. Okay, same thing. Clear that out. Natural log 0.0707. That gives me negative 2.65. Now, let's go to the next one. Clear that out. Natural log 0.05. Negative 2.99. I'll say negative 0.30, and so on. So you're going to fill all this data. Then you're going to go to your calculators, which you'll be able to do this on at least the free response section. If you graph this and it comes out to this line, we have verified that this is a first order integrated rate law. Okay? If it comes out bowed, it is not first order. It must be second order or zero order. Okay? So again, once we get this here, we need to compare this to this. Oh, by the way, this is time. And I'm sorry, this is concentration. Let's see. Concentration of N2O5 versus time t. Okay, time will always be on the x-axis. Okay? So, let's take a look at another. Let's see, what else does the problem ask us for? And it says, and calculate the value of the rate constant where the rate is negative and so on and so forth. So all we need to do to find the constant is take the slope. Okay? The slope is K right here. whenever they're asking you for the slope, all you do is rise over run. But be careful, because with rise over run, you don't want to deal with this data. It's the negative log, okay? So I would just take the two extremes. And let's do this, let's go down here and take the negative log of 0.00625. Oopsie. Negative log of 0.00625. We end up with negative 5.08. Okay, negative. So rise over run. Okay, so what's our x-axis and our y-axis? This is our y-axis, this is our x-axis. Okay, so let's take negative 5.08 minus negative 2.30 over 400. Okay, so this is natural log of the concentration, and this is seconds on the. This is natural log of the concentration, and this is over seconds. So what we have here is negative 5.0. Whoopsie, 5.08 minus a negative 2.30. This is negative 2.78 over 400. And that's negative 0.00695. Okay? So calculate the value of the rate constant, 0.00695 per seconds. Okay? So that's the value. That's how we would calculate this with a integrated rate law that is first order. Okay? Let me know if you have any questions.